Alright, now that we're done with chapter 3, so let's talk about application problem, like what might be the kind of example that you might come across that you can solve by using a Laplace transform. So this is actually a previous final exam question that I purposely selected for the purpose of showing you the application problem of Laplace transform. So here, this is the motion of a damped spring mesh system described by the following ordinary differential equation. So I have an equation of m d squared x over dt squared plus c dx over dt plus kx equal 0. First of all, when you come across equation of application problem, bear in mind, like, look for the variables. And for this case, we have our dependent variable is going to be x, independent variable is going to be t. Anything else other than x and t, those are not going to be variable, those are going to be constant. And I'm referring to these three alphabets right here, m, c, and also k. So they are constants, and the value is going to be given in the question. All right, and then so the represented the symbol of each of the like, what do you call that, like the representation of each of the symbols is being explained in the question. So it says that x is the displacement from equilibrium position, t is time, m is mass, and c is the damping coefficient. So now the value of the constants are given. It says that c equal 40, which is critically damped. The spring constant is k equal 20 Newton per meter. So you don't need to include Newton per meter in your calculation. Just pull out the value 20. And the value of m is going to equal 20 as well. So it says that find the particular solution for displacement using Laplace transform. So that has been specified over here by using Laplace transform. So, and the initial conditions are x naught equals 0 and x naught is going to equal 5. So x prime is going to equal 0 and x naught is equal 5. So the thing is that now, the first thing that you should do when you come across this equation is you should start by substituting the constants. So my m value is going to equal 20. So my equation is going to be 20 d squared x over dt squared. And then I have my c value. My c value is going to equal 4t. So I'm going to have plus 4t dx over dt. And my k value is going to equal 20 as well. So I'll have 20x, and that is going to equal 0. If you have a look at the equation, so this is actually a second order differential equation with the right hand side equal 0. So the Laplace transform is not the only way to solve this equation. So this can also be solved by using the undetermined coefficient. So this is simply going to be yc because it's a homogeneous equation. And then all you have to do is find the general solution and substitute the initial condition and find the particular solution. But because it has been specified in this question that we're going to use Laplace transform, so we're going to use Laplace transform. You can actually like start solving your equation like this, but I don't want to. I have like a very big constant values that I find that intimidating, and I'm going to get rid of that. So I'm going to divide the whole equation by 20 because I simply can. And the first term is going to be 1 d squared x over dt squared. 4t divided by 20, that's a 2. I'll have 2 dx over dt and plus 1x, and that is going to equal 0. We know that if you want to solve an equation by using Laplace transform, so the first step that you're going to do is you're going to Laplace both sides of the equation. So now let's apply linearity theorem. So Laplace of x double prime plus 2 Laplace of x prime and plus Laplace of x, and that is going to equal 0. So now apply the formula. So Laplace of x double prime, so that will be given by s squared capital X of s minus s x of 0 and minus x prime of 0. So this is formula for the Laplace of second order derivative. And then I'm going to have a plus 2, put a bracket around. So Laplace of x prime, according to the theorem, is going to be s capital X of s minus x of 0. So please refer to the appendix for this theorems. Laplace of derivative. And Laplace of x, remember this is not x, this is actually x of t. And when you Laplace that, it will become capital X of s. And Laplace 0, 0 is a constant. And we know that according to the table, if I were to Laplace a, that will be a over s. So 10 over s, that is simply going, 0 over s, that is simply going to be 0. And then the next step is to substitute the initial conditions. X naught, the value is going to equal 5. So don't forget to multiply that by s later. And this term is going to be 0. And this is going to be 5. and all the terms that are related to x of s, and I was referring to these three terms right here, so please put them together. So I'm going to do factorization. So I'm going to have x of s, so I don't want to use a red pen, give me back the black. So x of s, when I do the factorization, I'm going to have s squared from the first term, and then don't forget to multiply by the 2, so I'm going to have 2s, and the last one is going to equal 1, and then I'm going to collect all the term that is not related to x, and this term right here is going to be negative 5s, and this term right here, don't forget to multiply by the 2, it's going to be negative 10, and on the right hand side I'm going to have 0. And from here I can rearrange and write that xs is going to equal 5s plus 10, and that will be over s squared plus 2s plus 1. And we're not done yet, remember. So the question asks us to find what is going to be the particular solution for the displacement. Like, even if you don't read this, we can tell right away. Remember, when we solve a differential equation, we always look for the dependent variable. And for this case, we're looking for the function x of t. Right, so now all we have to do is Laplace inverse this in order to get x of t. I'm going to find the Laplace inverse of 5s plus 10, and that will be over. So check whether this is reducible for us to determine what method that we're going to use. And if you were to factorize this, you'll be able to figure out this is actually s plus 1 to the power of 2. And now that we have this form, that we're going to decide what method are we going to use. So actually there are two possible ways to do this. The first method is going to be partial fraction, and the second method is going to be inversion of the first shift theorem. But the thing is that I do not encourage you to use partial fraction when you have, like, if both methods are possible, so try to go for inversion of first shift theorem instead, because you know how tedious partial fraction could be. Like, when you do partial fraction, there's a very high chance that you're going to do mistake at doing the partial fraction itself, not doing the Laplace inverse, alright? So try to avoid partial fraction if you can. Like, if it's possible to use inversion of first shift, use inversion of first shift. That should be your first choice. Right, so now let's start with this. Okay, let me remind you inversion of first shift theorem by writing down the theorem. Laplace inverse of f of s plus a is going to equal exponential of negative at multiplied by f of t. So that's the theorem. And for this case, our value of a is going to equal 1. So my function f of s plus 1 is going to equal 5s plus 10 over s plus 1 square. And now I'll be converting this to the function f of s. All I have to do is, whenever I come across s, I'm going to put a minus 1 around. So let's see, where are we supposed to substitute? This one and this one at the bottom. So please make sure every single s at the top and the bottom is being substituted. Do not leave any of them. So here I'll end up with 5, put a bracket around, so it's going to be s minus 1 plus 10 over, so s, put a bracket around, s minus 1 plus 1 square, so which is going to simplify to 5s minus 5 plus 10, that's a positive 5, and that will be over s square. So that is going to be my function f of s. And then I'll be converting this to f of t. So my function f of t is going to be the Laplace inverse of this function right here. Okay, so that will not be, what I'm going to do is I'm going to separate them. I'm going to write this as a Laplace inverse of 5s over s square plus 5 over s square. So now this should be something that is familiar to you. I can simplify this, like, for which I'll end up with 5 over s. You know that this is going to be 5. And 5 over s squared, that is going to be 5 of t. So therefore, now that I have everything all together, I can write that. So therefore, so the x of t, so we're looking for xt. So xt is going to equal the Laplace inverse of 5s plus 10 over s plus 1 square, according to the inversion of first shift theorem, is going to equal, so when this is a plus, this is going to be exponential of negative, so I'm going to have negative 1t, so it's going to be exponential of negative t multiplied by 5 plus 5t. So that is going to be our displacement function. Okay, So basically, this is application problem is just revision of like the method that we have discussed before. It could be solving, could be simultaneous differential equation. Do not get intimidated by the equation just because we have alphabet from A until Z. So remember, only 2 of them are variables. The rest of them are constant values. The values should be in the question itself. Okay. Alright, so you should try the problem in the book or the extra exercise given by lecturers. And you can also find this in the previous final exam questions. Right, see you in the next chapter.